basically by doing what we did in like the last couple of units. If I need to find the actual solutions, find the actual roots, remember how we did that. We're going to start by making a list of our P over Q's. Okay. P stands for factors of which number? The last one, right, which would be the 8. So that's 1, 2, what else? 4, 8. And then Q stands for factors of the leading coefficient, which is just a 1. Not a whole lot of numbers are factors of 1, just 1. Okay, let's make a list of numbers that we have tested. Am I missing any terms in my synthetic division that I might need to write in a 0 for? Yes. 0x cubed. Any others missing? 4, 3, 2, 1. No variable. Okay. So setting up my synthetic division, we have a 1x to the 4th, 0x cubed, negative 11x squared, minus 18x minus 8. I'm going to switch to pencil now. Anyone need to go get a pencil? Everyone's just realized this unit makes us use a pencil. What number would we like to test first? 1? I know, I always do 1 and negative 1 first. Alright, trying 1, see if it's a 0. 1 times 1 is 1. Add, multiply. If I add those, I get negative 10. Multiply. Add. Ooh, it's not looking good. Not looking good. So is 1 a root? No. What should we try next? Negative 1. Okay, negative 1 times 1 is negative 1. If I add, I get negative 1. Negative 1 times negative 1 is positive 1. And when we add those, we get negative 10. Negative 1 times negative 10 is 10. And what do I get when I add those two? Negative 8. This one's looking better. Negative 1 times negative 8 is 8. And when we add, we get 0. Okay, so that one does work. Okay. If we started with a 4th degree polynomial, right now, what did we get the coefficients of? That's a cubic, right. How many more do we need to find to get it down to a quadratic? 1 more. We could try negative 1 again. We could try a different number. Anyone work ahead and find one that works? No? One else? No? 3? 4? 4 works? Oh, okay. Rhea worked ahead. Rhea said 4 works. Let's do it. So building a 4 onto there. Trying 4. We're going to bring down the 1. Multiply. And when I add, I get a 3. Multiply. When you add, you get 2. Hallelujah, multiply. Thanks, Rhea, for that. That makes our life a lot easier. 4 does work. Okay, so we found 2 that works, which means now this should be the coefficients of a quadratic. Okay, the 1 is the coefficient of the squared term on the quadratic, so that's x squared plus 3x plus 2. Now if we need to find the roots, that means we need to find the solution. So I will need to take this, I'll need to set it equal to 0 so that I can solve it. Does it look factorable? Does it look like we could factor it by solving? Yes or no? Yeah, I say it looks factorable. What 2 numbers multiply to 2 but add to 3? 2 and 1. And remember, for easy factoring, you can put those right in your parentheses. X plus 2, x plus 1. And then we'll need to still solve those. So we're going to take each little one. We're going to write a little baby equation. X plus 2 equals 0. X plus 1 equals 0. And we get x equals negative 2 and x equals negative 1. Oh, dang, we could have tried negative 1 again. Negative 1 again would have worked. So altogether we got, let's make a list of our roots. We had negative 1, which was a double. We had negative 2, and we have 4. -1 and 4 we took out as synthetic division. -2 and the other -1 were the ones we found using solving that quadratic. So based on those roots, based on those zeros, what would be the x-intercepts? Yeah, it's the same numbers. The x-intercepts would be -1, -2, and 4. Usually the only thing I do different for x-intercepts is I just write them as coordinates. So -1, 0, -2, 0, and 4, 0. Were any of those special?
Oh, I just had a question from the last question.
Sure.
I was like -1 double.
Because we took out 1 with synthetic division up here, and then we got it again right here when we factored and then solved. So that shows up twice. Which one of those was special? 4 was not special. -1. Why is -1 special? Because it's a double. -1. It's a double root. It's good to notice which ones are special, which ones are double roots, because they cause the graph to look slightly different in that spot. To find the y-intercept, how do we find the y-intercept of any function in the whole entire world? Plug in what for what? 0 for x. Very good. Plug in x equals 0. So that would be at 0 something. So we'll have 0 to the 4th power minus 11 times 0 squared minus 18 times 0 minus 8 equals, it's not rocket science, -8. Very good, because everything just kind of zeroes out, zeroes out, zeroes out. -8 is what you have left over. -8. Okay. Before we do in behavior, we have to kind of look at the bottom parts of the bottom part of the paper. Okay. In behavior refers to what the two end pieces of the graph are doing. Okay. Which way are they going? Are they going up? Are they going down? Where are they going to? And you can actually determine in behavior without having to graph the polynomial. Like before graphing, just by looking at the equation, you can figure out the in behavior. Okay. And it's all based on, two things. It's based on the degree, whether degree is even or whether it's odd. And it's also based on the leading coefficient, whether it's positive or whether the leading coefficient is negative. So the front number, whether it's positive or negative. Polynomials of even degree, as you can see in the table, have both ends traveling in the same direction. This is very similar to a parabola. If you think about a quadratic, a parabola, either both pieces of a parabola go up or both pieces go down. And it's the same for every even degree. So if it's a 4th degree, both ends will go up or both ends will go down. If it's a 6th degree, same thing. Both go up or both go down. Polynomials of an odd degree, there's a random plus sign here for no reason. Scratch that out, that was a typo. Polynomials of odd degree have ends traveling in opposite directions. And you can actually see that here. One goes up, but the other goes down. One goes up, but the other goes down. Have ends traveling in opposite directions. Now, the most common odd degree polynomial that we know already is a linear function. A linear function is an odd degree. Its exponent is, highest exponent is a 1, which makes it odd. And if you think about a linear function, it's either, like this, or it's like going like this, where one end is going up, the other is going down, or it's like this, where the other end is going up and the other is going down. I'm going to write that like a linear function. And it's the same thing for any odd degree. It's a 3rd degree. One piece will go up, the other side will go down. Okay. Now, if we look at how to figure it out, okay, if the leading coefficient is positive, then the right-hand end is traveling upwards towards positive infinity. But if the leading coefficient is negative, then the right-hand end is traveling downwards towards infinity. Let's see that in the table here. So if we look at odd degree, okay, so again, this would just be like a positive sloped linear function. It's going to go up as it goes to the right, and it goes down as it goes to the left. If it's a negative sign leading coefficient for an odd degree, it's just like a negative sloped linear function. The left side will go up, the right side will go down. And then for even degree, if the leading coefficient is positive, they both point up, just like a quadratic. If the leading coefficient is negative, they both point down, just like a quadratic. So if we look at ours, let's go look back up at it. What was the degree of this one? Degree stands for highest exponent. Very good. It's 4. Is that odd or is that even? Even. Okay. I'm going to write that down. It's even. Okay. And what is the sign of the leading coefficient? The sign of the front number? It's positive. Okay. Positive leading coefficient. I'm going to write LC for leading coefficient. Oops, sorry. There it is. Okay, so even degree means that both ends go in the same direction. So either both go up or both go down. Okay, but it is a positive leading coefficient, so that means both ends are going to point upwards. Left goes up, right goes up. Now, this is not the technical way to write the end behavior. We will come back to the technical way to write the end behavior. But for right now, we're going to use all the information we have to piece together what this graph is going to kind of sort of look like. Okay, just sketching it. So to piece together the graph, first thing we can graph is the x-intercepts that we found. All 3 of these were x-intercepts. So we can graph those 3 points. One is at -1, 0. We had another at -2, 0. And another at 4, 0. 1, 2, 3, 4. The next point we have that we can actually graph, we have a y-intercept that we found. The y-intercept was 0, -8, so we can plot that. Okay, and here's how we piece together the next part of it. We know both ends point upwards. Okay, so this furthest left point that I have right here at -2, anything after that, the graph should be going upwards, because I know both ends have to be going upwards. And the furthest right point over here, anything after this going right should also be going upwards. Okay, so I'm going to draw in the 2 end pieces. So anything after this -2 we know should be pointing upwards. Anything going right after the 4 should also be going upwards. Okay, and then we're going to put together the rest of the graph like a little puzzle. Okay. So all of these x-intercepts, I know it needs to kind of pass through there, but the only one that was special was -1. Okay, this is our special one right here. Now, how that looks different on a graph, let me kind of show you. Okay. If you have a regular x-intercept, so not a double, on a graph, what happens is the function just directly passes through there for a regular x-intercept. But for a double, what it does instead, for a double root, is it's going to tap it and it's going to turn right back around. That happens for a double root. So looking at -2, was -2 our special one? No, so I know it's going to pass right through there. But the next point that I have to get, if I'm working from left to right, the next point I have to get this -1 right here. So it's not going to keep going down and get this one, it has to get this -1 next. So it's going to turn back around and come back and get that -1. But that -1 was the special one, right? So when it's a special one, a double root, it doesn't pass through it, it just taps it and it turns right back around again. And I know it needs to turn right back around because the next point that I have to get if I'm working left to right is this y-intercept. So it's going to need to go downwards to get that y-intercept. Okay. And then the next point it needs to connect to is this +4 over here. Okay, so it's going to pass through the y-intercept and then it's going to come back and get that +4. Now this is just a sketch. Okay? It's not what the actual, if you were to look at the actual graph on a calculator, I promise you it ain't going to look like this. Because we don't really know how low it's going to go right here, so we're just guessing. I'm just saying, oh, it probably goes down a little and then turns back around. But it could go down super far and then turn back around. Same thing with the y-intercept. We're just guessing that it just passes through and comes back here. What it could actually pass through there and then keep going down super far and turn back around. That's why we're just sketching. Sketching is less accurate than an actual graph. All right, last thing we're going to do is we're going to write out the technical in behavior. Here's how you write technical in behavior. It has two pieces to it. The first piece says as x, and then there's an arrow, which means goes to, infinity, comma, f of x goes to, and then we fill in this part. And then the second piece says as x, arrow, goes to, negative infinity, f of x goes to, and then we fill in this part. Your technical in behavior will always look like this. The only thing we fill in is what goes in these two blanks right here. And we'll talk about what it means. Okay, when it says as x goes to infinity, that means as the graph goes to the right, okay, as your graph goes to the right, where is the y value, the f of x, going? As the graph goes to the right, where is the y values ending up? We have an arrow pointing upwards. So what would it mean that it's pointing upwards? Where's that going? Infinity. As x goes to infinity to the right, f of x goes to infinity, which means it goes upwards. And the second one is x goes to negative infinity. So as your graph goes left, where's the y value going? As x goes to the left, where's your y going? Well, it's also pointing upwards. Up. So that's positive infinity. For polynomial graphs, your answer will always be just positive or negative infinity right here. Okay? For other types of graphs, you might have an actual number. But for polynomials, it's just positive or negative infinity. So if it's going up, that's positive infinity. If it's going down, that's negative infinity. All right. This one took us the longest because we had to actually find the roots ourselves. But most of the questions on these, they don't make you find the roots. They write it in factored form already, making it the easiest thing ever to find the roots. It says find the x and y intercepts, identify the in behavior, sketch a graph so we can make it less technical. And this one is in factored form, which makes it super easy to find the x-intercepts. So if I think about what my roots are, or my solutions, this x plus 2, if I took it and set it equal to 0 and solved it, what would be its little solution? Its root? Negative 2. Okay. If I took x minus 1, set it equal to 0 and solve it, what would be its little solution? 1, so I know 1 is 1 also. Okay, and same thing for the last one. If I took x minus 3, set it equal to 0 and solved it, what would be that root? 3. So this helps me figure out what my x-intercepts are. I know one's at negative 2, 0, one's at 1, 0, and one is at 3, 0. Okay, we did the x-intercept. How do we find the y-intercept of any function? Not set it equal to 0. Set x to 0. Plug in 0 for x. Okay. This is probably the only thing that's more annoying to find when it's in factored form. But we also saved, 10 minutes not having to do synthetic division in factored form. So we do need to plug in 0 into all the x's here. So that would be negative 0 plus 2, 0 minus 1, 0 minus 3. Simplifying that, that would be negative times 2 times negative 1 times negative 3. What's negative 1 times negative 3? 3. And then we have just a negative times 2, which would be negative 2. Grand total answer, negative 6 is our y-intercept. Okay. I'm going to take all of these 4 points, and I'm going to put them on my graph. Negative 2, 0, 1, 0, 3, 0, and 0, negative 6. Negative 2, 0, 1, 0, 2, 3, 0. And then 0, negative 6 was the y-intercept. 1, 2, 3, 4, 5, 6. Okay. Now I'm not going to write my technical in behavior just yet, but I am going to see if I can figure out what the ins are doing. Can we tell the degree of this function? We've talked about this before. When it's in factored form, how do you know the degree? Count the x's. How many x's are there? 3, which means odd. Okay. which odd always tells me the ends go in different directions. I just got to figure out which of the different directions. The sign of the leading coefficient. Well, it's drawn in for you. What is the leading coefficient? It's -1. So we know the sign of the leading coefficient is odd, or negative. Come on, brain. Okay. So ends go in different directions. Its leading coefficient is negative. So I literally think about an odd degree function. I think about a linear function that has a negative slope. Okay, think about a linear function with a negative slope. Is it going to look like the first graph, or is it going to look like the second graph? A linear function with a negative slope. First graph or second graph? Second graph. Which means the left side needs to point upwards, the right side needs to point downwards. Same thing for this. Left side needs to point upwards, right side needs to point downwards. Just like a linear function. Alright, let's piece this graph together now. I'm going to start at my furthest left point over here. That's the one at -2. If the left side of my graph needs to point upwards, anything after this point will need to point upwards. Draw it in. On the right-hand side of your graph, that's the furthest one over, that's at 3. Anything after this will need to point which way? Which way? Downwards, according to this little piece right here. Okay. All of these were just regular old x-intercepts. None of them were doubles. We'll actually see on the next one what a double looks like in factored form. So all of these, we know it needs to fully pass through. It's not one where it just taps it and turns away. So I gotta fully pass through this -2. And if I'm working left to right piecing this together, the next point I actually have to get is not 1. What's the next point I have to get? -6 down at your y-intercept. So it's gonna go all the way down to the y-intercept. And then it needs to turn around because what's the next point in line that I have to get? The 1, the x-intercept, yep. So it's going to turn around, it's going to come back for the 1. And again, this was just a regular old x-intercept, so it's going to fully pass through that x-intercept. And it does need to turn around because what's the next one it's got to get? The 3. Okay. Just kind of, we're guesstimating about how high it's going to go. It doesn't really matter if you're just sketching it. Beautiful. We are going to write our technical end behavior now. Just remember there's 2 parts. As x goes to infinity, f of x goes to where? And as x goes to -infinity, f of x goes to where? And we only have 2 possible choices for a polynomial function. Either the y's are going to infinity if they're going up, or they're going to -infinity if they're going down. So looking at the first part, as x goes to infinity, meaning as it goes to the right, where are the y's going? -infinity, because they're going down. -infinity. Okay. And as your graph goes to -infinity, aka as it goes to the left, where are the y's going? Infinity, because it's pointing upwards, yep. Getting it? Okay. Find the x and y intercepts, identify the end behavior, sketch a graph. Can y'all see what makes this one special? Everybody see it? The square. What is that telling me about? No, you do not defoil. Don't foil it. That makes it worse. Don't do that. That's just telling me that the solution to this little factor is what? It's a double. Yeah, that's all it's telling you. So if I'm going to write out my x-intercepts, okay, we'll start with this -1. Okay, the solution to this would be -1. We know that it's what though? A double. I'm just going to write it down. Instead of writing mine as ordered pairs on this one, I'm just going to list them out. What would be the solution, the x-intercept to the next factor? +1. Okay, it's just a regular old one. Oh, I don't even need a comma if it's a regular old one. And then the last one would be 3. Very good. I have -1 that was a double because of the squared. +1 and +3 would be the solutions to both of these. The 2 is not one of the answers. The 2 is your leading coefficient, so it's what you're going to use to help figure out the end behavior. How do I find the y-intercept? Plug in 0. Let's do it. 0, comma, let's find the answer. 2 times 0 plus 1 squared times 0 minus 1 times 0 minus 3. That would be 2 times 1 squared. So that's 2 times 3, which is 6. 0, 6. Okay. Thinking about what the ends of my graph look like. I gotta find the degree. And then the sign of the leading coefficient. If we count the x's on this one, how many x's are there? There's not 3. Yeah, there's 4. This is a tricky one. This one counts twice because it was a double. 1, 2, 3, 4. The degree is 4, which is even. Is the sign of the leading coefficient positive or negative? Positive. Okay, so when it's even, I think about a quadratic. Either both point up or both point down. And if our leading coefficient is positive, that means both point up. So we know the ends are going to look like this, pointing upwards. All right, let's put all of this on the graph and piece it together. We have -1, we have +1, and we have +3. And then we have 0, 6 is our y-intercept. 1, 2, 3, 4, 5, 6. So I'm going to start with my furthest left point, which is the one at -1. Anything after this, according to my end behavior, needs to point which way? Up. Very good. Okay, and then I'm going to work with my 3 on the right-hand side. Anything after this is going to need to point up. Okay. Which one of these was the special 0, the special x-intercept? -1. Okay. So this is the one, it's not going to pass through here. It just taps it and turns around. So I know it's going to tap, turn around, and I know it has to turn around because if I'm working left to right, what's the next one it's got to get? It's got to get that y-intercept at 6. So it's going to go all the way up there, pass through there. What's the next point I need to get? The 1. So it's going to come back down. For the +1, does it need to pass through or does it tap it and turn around? Pass through. And I know it's got to pass through because what's the next point I got to get? The 3. Turn back around, get the 3. I'm going to speed run my end behavior. And remember, our only choices for filling in are going to be either positive infinity. Is it going up or is it going down? And both sides of our graph, the y's are pointing which way? Up. So both answers have to be infinity, positive infinity. Yep. Again, later on in further math classes, you'll be able to put other numbers there, but for us, it's just infinity. Like a weird eye twitch. All right, last one. Are any of these x-intercepts going to be doubles? Nope. What would be the first one? -3. And then -1, 2, and 5. So 4 x-intercepts, none of them are special because none of them have squares. The y-intercept, we're going to plug in 0. Let's see, 0 plus 3 would be 3. 0 plus 1 would be 1. 0 minus 2 would be negative 2. 0 minus 5 would be negative 5. So this would be negative 3. This would be 10. What's negative 3 times 10? Negative 30. That's not going to fit on my graph. There's two things you can do if it doesn't fit on your graph. You can just pretend like it's off the graph. You can also adjust the scale if you really want to. If you want it to fit on your graph, you can change the scale. It doesn't matter. Alright, let's get those x-intercepts graphed. Negative 3, negative 1, 2, 3, 4, 5. Do y'all want to just pretend like it's off the graph, or do you want to actually change the scale? Alright, we'll just pretend like it's off and just say it goes down there somewhere. What's the degree on this one? Degree is 4, which makes it even. So leading coefficient, positive or negative? Negative. So negative, even, which way are those ends going to point? Both down. Yep. Starting with the one on the left, if it's both pointing down, then everything after here is going to end up going downwards. Anything on the right after here is going to go downwards. All right, this negative 3, that's a regular x-intercept, so it's going to pass through their regular. But it does need to turn around at some point, because what's the next thing it's going to get? The negative 1. Negative 1 is next in line. And then after negative 1, we need to draw it kind of just going off the graph, because where's it going to go? Down to negative 30, wherever that's at. And then it's going to pick up, come back around, get this one. If you want to, maybe just write negative 30 down there, just so you know it's going down there somewhere. And then it's going to come back up. Got to turn around again and get this one. Do y'all want to do the end behavior? What's the answer for both the end behaviors? Negative infinity, because they're both going down, right?